So, hello everyone. Good afternoon, good morning. This is Ricardo Michaelis speaking from the CharIN Coordination Office. I'm responsible for our technical focus groups within CharIN. And today I'm proud to present you the Megawatt Charging System, mostly subgroup of the focus group connection. And the year is almost at the end, but I hope still everyone is excited for fresh input, new topics. And so I'm happy to hand over to Rustam Kocher, and which is the lead of this MCS team. And let's have a good session, and I hope everyone enjoys the presentations. See you later.
Welcome and good morning. Selamat pagi for those of you who in Indonesia and Malaysia. Welcome to the conversation about Megawatt Charging System. I'm here with a few of my fellow task force leaders and want to have a good dialogue with you today about how we got to where we're at and where we're at currently and where we're going. Next slide, please. My name is Rustam Kocher. I'm with Daimler Trucks North America. I work on the ecosystem and infrastructure team for the e-mobility group here at Daimler Trucks. We make Freightliner trucks as well as Thomas-built school buses and Freightliner custom chassis. So when we started this, almost a little bit over 2 years ago, we all sat down in a room together in March 2018 and decided that there was not enough power available in the current charging standards to do a fast charge for a commercial vehicle. Commercial vehicle is going to have 500, 600 kilowatt hours on the vehicle. And in order to get a true fast charge in 20 minutes or less, we were going to exceed any of the power capabilities of the current charging standards. So we decided that we needed to have a new one. And the only way we could do a new one was to work together to find a solution. Next slide, please. So we thought it was really important to build undeniable momentum and get enough partners on board that we could create so much momentum that it couldn't be stopped. And we really wanted to make sure that we could see the point of view of every stakeholder involved. And we didn't want it to just be the OEMs or just be the cord and connector manufacturers or the EVSE manufacturers at the table. We wanted to make sure everyone who was touched by this through the decision-making process had a voice. And so customers were very important, utilities were very important, they provide the power, the construction and design folks, the folks who are providing the network and charging, and travel centers that are going to host the trucks, folks like that. So we went through a pretty extensive requirements gathering process with everyone at the table. We came up with a requirements list. Next slide, please. And we built a list of requirements and came up with what we wanted this to look like. And so there we go. There's our list of requirements. So we said it's going to be a single conductive plug, that it will max out from a safety perspective at 1500 volt, 3000 amps. It would be touch safe, et cetera, et cetera. And so with those, we set out to come to find a solution and solicited submissions. And we're going to talk about where we are with that submission. And I don't remember who's next after me, but we'll pass over to the next speaker.
I think that's me, perhaps.
That's Paul. There we go.
Dino, so sorry.
Oh, no, it looks like Dino. We come to Dino.
All right, thank you. Hello and good day to our audience. I'm delighted to speak with you today about the genesis of the Megawatt Charging System. So my name is Dino Saucerides. I do mechanical design, engineering and engineering management for Tesla for about 10 years now. So for the last 2 years, I've been working with CharIN Commercial Vehicle Charging Task Force in the name of defining the next standard for commercial vehicle charging. So next slide, please. So first, I'd like to touch on motivation. So asking the question, so what, or why does this matter? So this matters because medium and heavy duty trucks account for nearly a quarter of all transportation related emissions in North America, and by extension energy use. So the dramatic effects of climate change are upon us, and electrified transport is the only way we know of to keep the commercial transport wheels of the economy turning without using heat engines, which burn fossil fuels and have a fundamentally limited thermodynamic efficiency, and necessarily contribute CO2 to the atmosphere. So while the grid may not be zero carbon now, it will be eventually, and electrified transport takes advantage of that forward motion. So with the stakes of climate change being high, and the interaction with commercial transport is clear. On the right side of the page, we sort of see what is ours to lose with this endeavor. So Black Mirror is a fun show about imagined dystopian futures, and one particular episode, it's called Nosedive, has the protagonist renting an EV for a road trip, comes to recharge, and lo and behold, her vehicle takes a different type of plug than what is available. And does anyone have an adapter I can borrow is what happens next. So the example below is probably more familiar, all the various implementations of USB, probably recognizable by everyone here. I'm sure they have their own strengths and weaknesses, which are all quite nuanced, but to most folks, this mostly represents an experience of, I have to keep several types of cords in my kitchen drawer because my bike light and my phone don't charge using the same interface, even though they could. So this is the world and the experience that we take into our task force meetings on Megawatt Charging System. And our measure of success is right there in blue, roughly stated. If it looks like you can plug it in, you can, and you can charge every time, no drama. Next slide, please. So while we're not prepared to post images of MCS geometry at this time, I wanted to share just a little bit of design strategies which a task force keeps in mind when talking through and executing on the design work of inventing a new charging standard for megawatt charging. So Tesla brings to CharIN our standard set of questions, including, is this limitation supported by physics? And why is this the way it is? And does it serve the end user? There were certainly discussions and whiteboard sessions early on, which sounded a bit like maybe we should just glue 4 CCS connectors together, but in the end, we were successful in challenging the status quo and what is possible, and looking to the future on where charging is headed rather than where it is today. So I'll illustrate that with a simplified example, which is that from a charging standpoint, for a fixed charging site power of 1 megawatt, charging a fixed number of trucks, let's say 10, at 1 megawatt in series will result in more drive time than charging 10 trucks at 100 kilowatts in parallel, because you get more drive time in the previous example. So notwithstanding logistics, dollars per mile will go down as charge power goes up, and ultimately gets balanced out by more nuanced things that I didn't mention here. But fundamentally, what that means is that charge powers we expect to be high. So the standard will be best in world on total power and up there with the Tesla standard on power density. We've challenged the status quo on thermals, and what that means is, how hot can it get and what are the follow-on effects of that? We're challenging power pin architecture, so what shape and arrangement is optimum? Communications, including asking if the task of communicating the charge protocol information is more challenging in the noise environment of megawatt charging versus kilowatt charging. And we've also spent several months refining a safety concept and are confident we're striking the best possible balance between absolute person safety while disbanding requirements which limit design but don't actually improve safety outcomes. Next slide, please. So you'll hear Andrew go into more detail about this, but one milestone worth pausing to celebrate is the in-person meeting which took place in September of this year, where about a dozen organizations took the MCS spec, in the in-progress spec, and independently designed connectors and charge ports designed to work at various power levels and came together to plug them in, essentially, and see how they charged. So with this, we're not only testing the mechanical design of the standard itself, but also how the spec would be interpreted and executed by multiple parties. So a perfect example of that is in the center there, is touch safety. Touch safety just means, are you able to touch the high voltage contact or not? So while the design as specified nominally solved for finger safety, meaning the IEC finger could not touch the live contacts, the standardized finger could not touch the live contacts, it turns out that was dependent on a particular interpretation of the spec. So the geometry was easily fixed in the next revision, and the spec was clarified, but the importance of that was really underlined by this in-person meeting. And then finally on performance, so while the CharIN spec will not specify a required performance, i.e. like will not say in the standards language must do 1,000, 2,000, 3,000 amps, because different use cases might require different amounts of current, or certainly will require different amounts of current. Sizing the connector and contacts, which is in the scope of the standard, does imply a performance limit, and the geometry should surpass the targets which the use case will require. And that's a complicated way of saying it needs to be big enough to support the currents that the use case requires. So going back to thinking about where technology is headed rather than where it is today, we did have multiple parties independently prove that the target of 3,000 amps is achievable within the physical envelope that we're working with today. So the plot on the right is an example of the type of data which was taken to prove that. That concludes this update. Thanks for your time. I think we're taking questions at the end or now, either one is fine.
And next up is Paul.
Including unmuting myself.
There you go.
Great. Well, thanks, and glad to join this evening and morning and afternoon, and for some of our friends making this go 2 in the morning in Europe. So thank you for everybody to help us put together and keep the slides moving. So let's go ahead and move to my first slide, which wasn't the one I thought, but that's okay. We're still good. So I'm Paul Stith with Black & Veatch. Been with Black & Veatch for coming up on 6 years now, and I'm Director of Global Transportation Initiatives. So it's really looking at all the things that Black & Veatch can bring to the picture. And if you're not familiar with this, so we're a global organization. I'm kind of cross those groups now with the Growth Accelerator, looking at power, looking at communications, certainly the whole renewable energy, and then we do a tremendous amount of work, particularly in Asia, in water. So all of the things that municipal interests are needing with in regard to water. In charging, we're coming up on about 8 years in working in particular in this space, and that kind of has involved a tremendous amount of work with Tesla, Electrify America, transit across the United States, and some of the most interesting places, New York, Washington, D.C., and Rochester, New York, for example, bringing these kinds of high-powered charging things to the scene, and sometimes the first time. So we've been really excited to be participating in CharIN over the last couple of years, bringing our expertise and really, what does it take beyond the charger? What is that ecosystem, if you will, that's going to be needed to make these things successful? So go ahead to our next slide. And I'm gonna, our other colleagues are very technical, right into the weeds of the couplers and what's going on there and the really smart stuff, actually, of course. I'm gonna be kind of doing mega trends, if you will, and then dive into some of the project-oriented things that are needed for these types of projects. So we're very fond of, looking ahead, and I would say that the trend towards zero emission in this case, is really an important one to be supporting, and it's kind of around that wheel of sustainability, all the different things that corporates are doing these days, and they may be driven by environmental, by social, governance, and their priorities, but frankly, it'll also be driven by finance, which is really, really handy and convenient for electrification, of course. If we go to the next slide. So in the trends, or going to call them kind of mega trends, things that we're seeing, frankly, this is a moment that many people in electrification have been waiting for. And if you'll jump to the next slide, the kinds of infrastructure that are going to be needed to support what these vehicles are going to be looking like out in the field, including conveying so much power and energy into them, it's going to kind of shake things up a bit. And that, frankly, is that if you are not electrifying, you're going to be left behind. So that's a really important thing. And as we look at the grid, getting involved and getting access to that power is very important. Let's do the next slide. Along with what's happening in the decarbonization of the space, of course, what's happening in the data side and the sensors, and I know, in fact, Daimler has some announcements, and many do, of course, as to what's happening with the data to make these vehicles move autonomously, to save lives, to also back to the economics of it, and create optimal efficiencies. And I think we'll have some talk about automation in our panel here. Next slide. So with the data, you're going to need that infrastructure, of course, that's behind the scenes that's making that happen, and moving it around in a lot of interesting ways and processing it. So coming from vehicles, moving to vehicles, controlling them. We're doing a lot of conversations, as you'll see, in the airspace. So if you move to our next slide. The energy that's feeding into these vehicles, of course, we haven't accomplished anything unless it's renewable. So how it's going to be manifest in centralized and decentralized generation, we see that is really, really going to be an incredible, important ingredient. And if you go to the next slide. And in the transportation spaces, if you start to look at these energy draws, the vehicles, the buses, the large trucks, they're going to be very similar to the energy density, for example, that's going to be needed in aviation, particularly conventional takeoff, landing, and eVTOL applications. Let's go ahead and move to the next slide. So those are some of the mega trends that are going on, and how are we going to get to this electrified future in this particular segment with a plug that's coming. So let's move to our next slide and talk a little bit behind the scenes about the driver to that. For example, as these battery technologies go up, we're opening up these new applications. So it was regional haul, shorter haul, cities into longer haul in regard to trucking. Well, every time you go ahead and, of course, increase the battery capabilities, we also have to invent and keep up on the ability to fill those batteries. So higher power charging clearly is what we're here today talking about, but it also means in that ecosystem there's going to be much larger power delivery, we talk about a lot, capital requirements, and then making sure you're investing in planning out those sites in a least regret fashion. So the types of facilities are going to certainly also be very interesting as we move forward, and there are going to be a lot of things that are similar. In fact, we're going to see potentially where they converge in some places. Let's move to the next slide. Each of those types of scenarios requires really to get all of these things, every icon on this map in line, and it's going to hover over the asset utilization and the revenue, and it has a lot to do with turning these vehicles back out onto the road, but also the charging themselves, chargers. What is the utilization of, say, 10 chargers versus 100 chargers in a depot, or some blend of those? So I think that's something really important that we're definitely going to be needing to explore and continue to get the right balance of charging capabilities and having flexibility, which is something I know that MCS has been working towards. Next slide. So in the real world, in order to bring this kind of power to site, you're going to need to be more or less become a understanding, I'm going to use the word, and respect what it takes to bring power to site or generate it on site. And that's going to follow really some timelines that are just traditional. And in the built environment, it's been going on for an awful long time. Talk about data centers and others, and even interconnecting, say, a large solar field. They're pretty used to this. In our EV young years, we like things to happen a lot faster. So respecting what is needed is going to be something that's there, and also that every site is different. That when you're looking at sites, the grid, the building may be the same, the layout could be the same, but the actual site is in a different position on the grid, even a different utility perhaps, that has different built standards and different capacity available frankly, compared to maybe your neighbors who also may be interested in deploying these technologies. Let's move to the next slide. So a couple of things that are important when we're talking about sites that are going to grow in size and programs and projects is that changing things midstream is not such a good idea. We're talking about deploying, charging cabinets. We're talking about bollards and things to protect it. Some pretty, heavy lifting, I'm going to kind of say literally, in those sites. So changing that midstream, re-engineering it midstream, not planning ahead, those things are actually very expensive. So we want to look to avoid that. And we're going to find that more and more of these projects, it's going to be a comfort zone here, but the same rules are going to apply. You can't really change, you need to plan ahead. And a lot of it's going to be about space and about capacity and frankly, the calendar. Do one more slide. So in the realm of fueling vehicles, there's going to be and read the next slide. There's going to be an awful lot of different ways that this manifests as to how the vehicles are, infrastructure is brought in place, how they're fueled, and that's something that happy to talk more about. But I think the thing to focus on this chart really is the speed to market, that those first movers getting access to the technologies, learning what it takes to deploy them, that's just incredibly important in order to iterate more quickly to learn and understand how to make this happen and as you go to scale. So I'm pretty much done for here. So I've got some resources that'll be in the slide deck. Let's move on to the next speaker and looking forward to questions.
Fantastic, thanks, Paul. So after Paul is Kevin, and while Kevin's getting ready, I just wanted to remind everyone that we will be having questions after the presentations are over, but you can start typing them into the chat function now, and we'll go through those when we're finished. So take it away, Kevin.
Well, yeah, thanks very much, everybody. Honored to be here and honored to be part of the MCS task force at CharIN. It's really great to work with such a great group of people. It's been exhilarating for Power Hydrant and myself, so thank you for all that. Next slide, please. Yeah, so Power Hydrant is a startup in the Boston area in Massachusetts, USA. We're approximately 4 years old. I myself spent the majority of my career in the semiconductor industry, and the semiconductor industry is interesting because while it clearly is at a lower scale on a systems level compared to the automotive system, it is a very important part of what's going on in automotive systems, and it's a great place to view what was going on in the future. And it was clear to me and many people at Analog Devices that automation in mobility was going to be important and electrification was going to be important. And that really is the motivation behind what Power Hydrant is all about. We asked ourselves 3 questions. How are we going to autonomously charge things like robo-taxis and other autonomous vehicles in the future? How are we going to fast charge very large vehicles that need to quickly charge just to be relevant, just to be useful? And how are we going to enable fleet operations? And these fleet operations are not simple things like plugging in your car every evening before you go to bed. It's a big industrial concern to keep these vehicles going, and charging these vehicles as they're electrified will be part of the operation, and that should be automated. It should be designed to optimize the utilization of assets, and it should be made as reliable and as measurable as possible. So those were the 3 big motivators that drove us. Next slide, please. So this all led to Power Hydrant, and as a background to Power Hydrant, I should point out that there's a phenomenon going out there called the mobile phone dividend. And in simple terms, we all live with mobile phones, maybe even multiple mobile phones in our day, every day. And these are really high performance devices. They have high performance CPUs, they have high performance sensors, high performance image sensors. And these devices have been commoditized by virtue of the sheer size of the mobile phone market. So that computational and sensing capacity finds its way into a wide range of applications that are looking for commercialized, ready to go to market core technology, but importantly, ready to go to market technology that is very low cost. So even though the image sensors that are in your typical mobile phone are just amazing from an image sensing dynamic range of light point of view, they are in fact relatively inexpensive and appropriate for reapplication. And that's exactly what Power Hydrant is doing. It's reutilizing key elements from the mobile phone sector to enable a computer vision robot. In addition to all that, a lot of the electromechanical elements of Power Hydrant are utilizing fixtures that are also commoditized. So what is Power Hydrant? Well, it's an autonomous robotic solution. The solution that we're showing here is a SCARA robot, and what's interesting about a SCARA configuration of a robot is that it actually only has 1 degree of freedom that has to move against gravity, and as a result, you can enable this robot with very light duty motors, and that's something that we do, and it's important that we do that in order to keep costs down, but also to make it appropriate to work with human beings, so that even in the most extreme pathological worst case that the robot moves and actually bumps into a human being, it's so low power, it's really going to have no impact on that human. And that's one of the key cobot requirements for anybody familiar with the cobot world where robots are working with people. The foundational element of it is that these are really low power robots and won't hurt anybody implicitly. But in the use case that we're focused on, Power Hydrant is intended to be an autonomous robotic solution. It's cost effective, but even though it's cost effective, it can be made to be physically robust. We're showing here a ground mounted unit, and that ground mounted unit is built from ductile iron. The primary bollard that you see there is the equivalent of a bollard that you might see protecting EV equipment in a parking lot somewhere in the world. And the rest of the solution is very, very durable. It'll survive an engagement with a snowplow, as we say here in the Boston area. Here we have an image of it with a Tesla semi, and you can see a synthetic pool of water shown there. And that shows the range of movement for the robot. As long as the inlet port for the vehicle is in that pool of water, we can gain access to it. And then we show an image next to the very well-known dispenser unit for a Tesla supercharger, just to give you a sense of size and scale for the robot. So the robot's not small per se, but it's very comparable to what we're used to seeing in EV infrastructure applications. And then it's not necessarily relevant to today's subject, but there are many areas of autonomous electric vehicles that we're provided opportunities with. And one is the AGV, the autonomous guided vehicle market. These basically are autonomous forklifts and autonomous factory vehicles that require charging. They may not require charging at a 4.5 megawatt rate, but they still require charging at very high power levels and need autonomy to do that. So next slide, please. So here's a photograph of the Power Hydrant unit that we brought out to Golden, Colorado for testing, just as it was getting ready to be packed up. I have obfuscated the actual connector section since it has some proprietary MCS details that'll be revealed, I guess, sometime next year. But the key features that you're seeing there are the vertical bollard, that again is a full heavy duty bollard. Then there are 2 robot arms that help form the primary range of operation for the system, and those are fabricated again with ductile iron, very heavy duty, very rigid. Ductile iron is a fairly inexpensive metal to fabricate with, so it's appropriate for keeping costs down. And then that all connects to a vertical arm system going down to the connector, and again the connector is obfuscated there. An important element of the design is that we've actually implemented a passive suspension system at the interface between the vertical robot arm and the upper arm of the robot. And the reason for that suspension system is that in practice, the vehicles that we're connecting to will be buffeted by wind. They may be actively loaded while we're charging. And at a minimum, drivers may in fact be getting on board the vehicle and there's a very good chance that the chassis of the vehicle will be moving dynamically. So the robot is a very rigid, strong device, but we have to provide a soft interface to the physical world that we're connecting with, and that's how we're implementing that with an active suspension system. We also have designed this robot so that it can be manually operated, believe it or not. So there's a green handle you might be able to see. It's vertically aligned. That green handle can be grabbed by the operator of the system and actually guided by hand to the inlet. And this is a requirement of the MCS requirements document, but it also is a very useful thing in extreme cases where the robot may have difficulty finding the inlet port. And then a little inlet image, inset image that I show there is a cross-sectional cut of our vertical arm that's able to carry well beyond 3,000 amps. And what I'm showing there is that we're using aluminum bus bar set in a die-cast material holding an aluminum oxide carrier. That ends up creating a very nice environment for carrying high amperage. Now, aluminum isn't the first choice when people think of high amps. Copper is always the go-to conductor, but the economics of aluminum are very, very interesting. They're about 1/6 the price of copper per amp carried. And when you're building a rigid bus bar system, aluminum is a usually preferred place to go for economics and reliability. And in our case, we end up with a very nice dense structure, and the actual conductors become part of the structural element of the robot in this case. So it's a unique side effect of going autonomous is that you can actually reduce some of your fundamental costs. So next slide, please. So here we show the robot in place in Golden, Colorado at the NREL Laboratory, National Renewable Energy Lab. And just a shout out to the folks there. They did a really, really nice job helping Power Hydrant out and everyone else out running the tests that they did there. It was really a first-rate effort, and they should be applauded for all the work they did. You can see one of the horizontal arms extended out, holding up the vertical arm, and that's connected to an inlet port. That inlet port happens to be a Power Hydrant inlet port, but as the testing went, you could connect to other vendor inlet ports as well. This is a shunted inlet, so where it's an amperage test. And on the right side of the slide, you can see a FLIR infrared image, which is very dramatic. The scaling of the infrared colors is such that it's appropriate to be dramatic. But in fact, those temperatures are really, really fairly low. So we're running 1,000 amps, and the highest temperature in the robot assembly is on the order of 40 degrees Celsius. So we're very happy with our structure, and it's probably worth pointing out that we're not doing any kind of liquid cooling at all in the robot. This is all passive cooling, and that is our strategy for all the amperage levels that we're planning to go for. So next slide, please. And then this is a little bit of the data that we extracted and provided to us by NREL. Again, a very professional set of data collection on the part of the NREL team. Congratulations to them. And what was nice about this data in particular for us is that a big focus of what Power Hydrant is all about is reducing source resistance. It's a simple, maybe even boring topic, but it's a key enabler for us to open up the window of being able to transport massive amounts of power to target vehicles. And it was really nice the way NREL put the data together, basically determining a total source resistance, including some instrumentation elements that are part of the power chain that we dealt with. So we're in a very good position with the standard in terms of getting good data from the system and from the testing very early on. And I believe Dino alluded to this earlier that we're really getting excellent data very quickly in the evolution of the standard, and this is emblematic of it. I don't have a slide about it, but I'll also point out that in the ergonometric testing, which really tested what range the cables and robot systems that were tested could reach. There was equivalent excellent reporting and excellent exercising of different test conditions that were very, very appreciated by everybody that's received that data. So next slide, please. So just a little glimpse into how we do computer vision. I mentioned that we're utilizing and exploiting the mobile phone dividend, the smartphone dividend, if you will, where we're utilizing low-cost image sensors with great performance. We happen to be utilizing a 3D image sensor to do an augmented reality type of computer vision. And if you look at the diagram on the left, this really outlines how we're doing this. First thing we do is we communicate with the vehicle we're connecting to, in this case, a Tesla Model S. We communicate to that vehicle and we ask the vehicle what the vehicle identification number for the target vehicle is. That communication will either happen over any one of the emerging vehicle to infrastructure communication standards that are evolving. And in the most extreme case, it'll be connecting to just a Bluetooth dongle that will be in the target vehicle. So we'll learn the vehicle identification number of the vehicle. We will look up in an edge stored right in the robot library of solid models. We have over 10,000 solid models of vehicles in our library. We look up in our local library for a solid virtual model, basically a video game piece matched to that vehicle. And I'll talk a little bit more later about where we get those models, but safe to say there's a large industry providing those models. So once we have the model, we then take a 3D image of the scene that we're looking at. In this case, we're using stereoscopic images, and we have a 3D extracted image that we then align to the virtual image. And with that, we find out two things: where the inlet port is and where not to move the robot so that we don't run into the vehicle. So, and all this is done within the robot. So next slide, please. And then a quick show of our connector. We have a unique pulling mechanism for our connector where the connector actually pulls itself into the inlet. And this makes for much more robust connection systems going forward. So that's the end of my presentation, and I'll take questions later. Thank you very much.
Thank you, Kevin. And next up, I believe we have Andrew from National Renewable Energy Laboratories. You've heard it mentioned a couple times as NREL. Everyone likes to shorten it up and make it easier to say. So off we go, Andrew.
That's perfectly fine by us. We refer to ourselves as NRELians, so no worries there. Thank you, everyone, for the discussion thus far. I guess I'm on the home stretch to bring it home. So if you'll go to the next slide, wanted to introduce myself and NREL and what we are and why we're involved with this discussion. Really, the National Renewable Energy Lab is a lab part of the U.S. Department of Energy, and so we focus on energy efficiency and renewable energy across a couple of portfolio areas. But the science that we look at is focused on wind and solar and water power. I myself work on sustainable transportation that includes electrification as well as bioenergy and hydrogen. We have a fair amount of work in energy efficiency for buildings and manufacturing. And then, of course, also near and dear to my heart is the discussion about grid integration and how EVs or vehicles can play a role in that world. So if you go to the next slide. Yeah, so digging a little bit deeper into the transportation technology space, we really see that maybe the next frontier, or I don't know if we want to call it the final frontier, probably not, but the discussion about electrification for medium and heavy duty vehicles is really very interesting from the carbon perspective and from the overall energy utilization of these vehicles, as Dino alluded to in his first slide. And so we're interested in this evolution and thus this discussion about the electrification of at up to megawatt or greater charging powers for these vehicles. And it really helps with this discussion about getting electric vehicles at scale and throughout all sectors in the space. So go to the next slide. The MCS evaluation event, I wanted to provide some additional detail, kind of dig into a couple of the topics for the group here. Basically, we started, initially we planned to do this in the May timeframe, but we're able to pull off a successful event this fall, end of September. We had about 12 different in-person participants, as well as 51 virtual participants. And we have a pretty good wide variety of people within the field. So you've heard from a couple of the hardware participants, Daimler and Power Hydrant and Tesla earlier today. And so what we were trying to do, or what we are trying to do with this, was to pull together this broad view of industry and try to help each of the individual entities test their components together. So as we work through this development of a charging standard, we want to make sure that it works in a way that all industry participants are able to be able to plug in and charge, right? It's got to be simple, it's got to be easy, as was discussed before. And so how we did this was through initially 2 test events. The first one we called the Fit and Ergonomics event. We had 5 cable systems and 4 inlets. And then the second one, which both of these I'll go in more detail, was the functional evaluation or the thermal evaluation. And so we tested up to 3, what we call 3 different levels for this, up to 350 amps and a passively cooled system on both the inlet and the connector. On the level 2, we were doing active cooling on the cable in some cases, passive in others, but passive on all cases in the inlet. And then level 3, up to 3,000 amps, was active cooling on both the connector and on the inlet. So with that, I'll go to the next slide and we can dig a little bit deeper into the Fit and Ergonomics event. As Dino mentioned earlier, part of this effort was to provide the design requirements to each of the manufacturers and have them build their prototypes based on that information. And a lot of the interesting outcomes from this Fit and Ergonomics event is how each of these systems made it together, what some of the interpretation of the design versus how it was actually built, and how others interpreted design, how those maybe clashed in some cases. And we had some good learnings. Dino pointed out the discussion about touch safety. There were other discussions about surface finish and the design of specific features on the design in order to reduce the insertion force and make the connection process much more simpler. And so in the kind of the next part, the ergonomics portion of the discussion, you can see in the picture in the left, we built a test stand in which we mounted each of the inlets. In the lower corner of that picture, you see the ability to tilt and then raise and lower that system. And so that allowed us in this event to kind of understand with multiple participants of different heights and builds, how easy it was to plug in the system. We also looked at, as you see in the picture on the right, the connection point as to where the connector was mounted, how high up above the ground it was mounted. And so this allowed us to understand some of the issues with regard to maneuvering the cable to get it into the inlet, and flexibility in its overall design of the mounting features. So really the kind of the goal here on the ergonomic side was to to get the engineers, I'd say, out of their office, but in this case, out of their homes and into the lab, and be able to touch and feel and understand how the overall design would work in the built environment. I guess I should also mention that we did evaluate the automated system in this test setup as well. And so with all of these different configurations, it really allowed us to understand some of the refinements that may be needed in the standard in order to make it very easy to be used by the end user. So if you go to the next slide, we'll dig into some of the thermal analysis or the functional analysis. So this is a picture on the right of the level 1 bench, the passively cooled systems. So this allowed us, we had 4 connector systems and passively cooled inlets. This allowed us to evaluate the thermal temperature rise of each of the combined components. And so what we did in this event is we changed the connectors and the inlets and compare and generated data to allow the manufacturers to compare the overall resistance rise across multiple inlets. And so this is allowing an understanding of how the resistance changes over time, but also how it changes with different connector systems. And so the data from what we're doing here will allow each of these manufacturers to refine the design and understand maybe some of the pinch points and what the overall technology is able to do. So if you go on to the next slide, the level 2 and level 3 actively cooled bench. This is very similar to the passively cooled bench, except for we were able to get up to 1,000 amps in the level 2 case and 3,000 amps under the level 3 case. Again, temperature rise and resistance change were measured over the test duration, but given that this is an actively cooled system, we're able to at least measure how much heat rejection is required and to provide that additional information on the performance of the system relative to the electrical parameters and then the temperature measurements. And so we're able to, in this test bench setup, measure the ability of the inlets, of multiple inlets and connector systems when they're mated together to be able to understand the different capabilities. We also, in this test setup, we're able to evaluate some passively cooled systems. So if we go to the next slide, where we are, so that's what we've done in 2020, and we've gotten some great learnings. But where we're headed in 2021, I wanted to touch on that briefly. We expect to repeat or improve on our initial analysis of the active and passive cooled functional evaluation in 2021 based on some design refinements. We're also intending to look into quantifying the insertion force in a much more rigorous manner to include wear out mechanisms, vibration, and other mechanical analyses that would be done with the design. We're expecting to potentially look at the electrical resistance differences from these different designs under temperature, as well as the insertion force. And so we're hoping that this additional information will provide some good insights on how the device will perform, not just in the prototype stage, but in the more built stage. And finally, another effort that we're looking forward to is some additional work on the communications and noise injection discussion with the system. And so we're hoping to analyze these connectors under voltage and current, not just current as we've done in this first year, to understand some of those constraints and basically demonstrate that you know, we're able to transfer the real power that everyone's interested in. And so with that, I think that's my last slide. So we can, if there are any questions, I'm happy to answer them. I didn't get the 0-minute picture, so.
Didn't quite get there.
Didn't quite get there.
At this point, I believe we are at the question and answer phase of the proceedings. So if all of the speakers would turn on their cameras. And thank you all for presenting tonight, or this morning. And I'm seeing some of the questions come in. Again, please pose your questions through the chat, but most of them are centered around the timing of when will this be ready. And there's a couple pieces to that. So as Andrew touched upon or expanded upon, we're in the process of doing fairly extensive testing of these designs. We learned a lot from the most recent event that we held in September. We've taken learnings from that event and applied them to the design. We've gone through another iterative process from there, and then Dino, maybe you can expand on where we are now, and then we can jump to Andrew as to when the next one's planned.
Yeah, I think that actually captured it pretty well. So we're in the sort of a final iteration phase, just sort of tying a bow on the things we learned in at NREL, is particularly around, you know, finger safety and ergonomics. And yeah, I think then we come back one more time at NREL, and then I think in Rustam, maybe you want to say more about this, like the ultimate plan for what happens to the specification with the SDOs.
Certainly. So Andrew, maybe you can talk about the process we're going through for the next round of testing, and then I'll hit on the timing.
Yeah, so right now we're in the process of working with the hardware partners who came in the first round, and working with additional ones to try to identify what features of the test we did previously we should expand upon. I'm expecting that process to occur over the next month or so, and we're looking for an early 2021 evaluation, maybe of the thermal portion. We might end up splitting some of the aspects depending on the different characteristics and some of maybe the lab restrictions. But yeah, we're in the process of moving forward with additional testing along some of the similar lines that I presented on.
And I must say that doing all this with really stringent COVID restrictions in place has been circus-like in all the different steps we need to take. But we've made it happen. We proved that a hybrid event is feasible and viable, and we're ready to do it again. In regards to the next steps after that, we are prepared to go to CharIN is not a standard setting organization. They have hosted this task force, and they have hosted this work that's been done, but they are not a standard setting organization. So we will go to a standard setting organization, present this document and this completed design, and the intention is to move it quickly through the standards body to a final completed standard. We know that that doesn't happen quickly in most cases, but we plan on having all of our T's crossed and I's dotted, and we'll have a design fully tested and validated and ready for the world to see. So we're hoping that can move through the process quickly. There was a question I saw about robotics. So Kevin, has there been any thought into roboticized charging of marine vessels that move while berthed?
Yeah, that is definitely on our list of markets to pursue. We are a startup, so we are constrained on resources, and so we don't have any published plans in that domain. But that's certainly a market that we're interested in, and I know that ABB and some other vendors have shown robotic solutions for marine vessels as well. So it's an interesting area for the industry in general. It's interesting for Power Hydrant, but no published plans. I will highlight that marine vessels have special care abouts, and one is there's an awful lot of motion on the vehicle, even if the vehicle is like a ferry vehicle and a portion of the dock mechanism is actually mounted to the ferry. There's still a lot of motion that has to be compensated for in that. So that's something that requires special attention. But it's definitely a market that we're interested in, and I'll highlight that we're also pursuing CCS2 and CCS1 solutions with Power Hydrant, and then I showed an image of AGVs, and eVTOLs are also an interesting market for us, but nothing published in the eVTOL or marine vehicle domain.
And as we delve into that portion with the eVTOL and marine, I will say that we went into this attempting to solve commercial vehicle charging, thinking that it was buses and trucks, and rapidly found out that there was a great deal of interest in other industries, similar, aircraft and marine as well. So I think when MCS is finished, it will not simply be a commercial rolling vehicle charging standard. It will also be flying and waterborne, as well as potentially others. And there's a lot of interest.
Yeah.
All right, questions are rolling in. Oh, we've got a couple polls. So Ricardo, if you want to throw the first one up, and we can kind of see what the respondents have on that one. So do you find that your current charging options are limited or due to current charging power levels? Simple yes or no question. And while you guys are answering that one, the next question to Andrew and Kevin is, the level 2 NREL testing shows only active cables, but Power Hydrant showed testing at near 1,000 amps with passive cooling. So can you describe how we achieve that? So the respondents, we've got about 60% show that they did find that their charging options were limited due to current power charging levels. So it's about right. There's certainly applications that don't need higher power and quicker charging, but there certainly are some that do need it, which is why we're pursuing this. So in answer to the question of how did Power Hydrant achieve 1,000 amps with passive cooling, Kevin and Andrew.
Kevin?
Yeah, sure. Well, I think the key thing for us is that we have a very high ampacity in our conductors. As I mentioned, we're using aluminum, which is has lower conductivity per square area than copper, but we compensate for that by using a larger square cross-sectional area. And our ampacity is designed to be very high, number one. And then the insulator that we use is StyCast, which is a technical, it's actually a brand name, but it's a technical epoxy that is filled with aluminum oxide. Aluminum oxide is an insulator, but it conducts heat relatively well. So between high cross-sectional area in our aluminum conductor and our very good thermal performance in our insulator, we can shed heat very nicely with our solution. So that's how we do it. So it's as simple as a big bus bar carrying our amps. And then at the actual contact point, I don't think this is proprietary information, but we're using the MCS standard is a so-called tuning fork style contact solution. We actually have a heat pipe filled with deionized water that carries heat away from the actual contact area to an area on our bus bar that we know is going to be at a lower temperature. So in one particular area where we know we will have a hot spot at the contact, We draw that heat out with a heat pipe. And if anyone is curious, virtually everyone's laptop and tower PC in the world have heat pipes to draw heat away from the processor core that's there. So they're ubiquitous, they're low cost, they're hermetically sealed, and they will work forever.
Very nice. Next question. It sounds like backwards compatibility with existing CCS plugs will not be supported on the new MCS inlet design. Is that correct? So I'm going to throw that one to Dino, and then as a follow-up to that, I want to ask Paul about the conversation we had about another topic that was very heated on this, similar to this backward compatibility, which was the location of the inlet on the vehicle. So take it away, Dino.
Yeah, so that's largely true that MCS will not be backwards compatible with CCS. So if you're talking about a straight pass-through adapter where all functionality is identical, the only difference is geometry, that definitely is not the case in this. The reasons are technical, but essentially come down to we were able to design a safer overall system if we let go of the compatibility system, and that safety is always a primary concern. A secondary reason, which is really still being investigated, is the fitness of PLC at megawatt levels of charging in terms of noise. That's an unknown at this time, to be clear. That's not to say that it is impossible. There are certainly someone could certainly imagine an adapter which speaks the language of either side to the vehicle and the charger. Such a thing is certainly not precluded. And having both inlets on your vehicle, CCS and MCS, would also not be precluded, though perhaps costly.
All right, and Ricardo, why don't you throw up the next poll while Paul answers the inlet location question.
So I'm going to just start with, and this is the raise your hand, but really to think about it is how many places do light duty vehicles have and how many places do buses perhaps have on where they charge. And that could be, and just as this is what we've driven, I've driven a Leaf that was in the front. I've driven, we had a Honda Fit, was on the front fender. We had a RAV4, was on the reverse, on the back quarter panel. I drove a Mini E, was on the other side, if I remember right. And now presently we've got a Chevy Bolt. So if you're going to be charging really heavy duty vehicles that take up a lot of real estate in and of themselves, you can start to appreciate if you allow that port to wander anywhere on the vehicle, and you've got the cables that are going to be quite a bit more substantial and a few different things. So in the end, it becomes really an imperative that port be in the same place. Now, if you want to argue for a few months or discuss politely, however you want to phrase it, then you can decide where to put it on the vehicle. Because those discussions certainly have been had upwards, downwards, sideways, and I don't know, Rustam, if we're describing where that'll be, but really it's the physicality of the design that creates a bunch of challenges.
We have published it, so be it what it may, it took us 1.5 years to get there, and I'm proud to say that we've said that it is behind the most forward axle and in front of the most forward rear axle on the left side of the vehicle, which is to say near the driver's side door on the left side of the vehicle in Western markets.
To that, we've also debated about right-hand and left-hand drive, and was that actually settled yet?
It was settled. So in the end, we said left-hand side for all markets in order to help the designers get the power to the inlet and to the batteries in a safe and secure and cooled manner, knowing that inlet was going to be on the same side of the vehicle for either side market, and we said left for both markets.
Yep. And I'll add on something to this, and this is really when it comes to building this infrastructure, you kind of are either it's going to be an island the vehicle will pull through, or you're going to pull usually forward in. So there are operators that operate these vehicles that don't drop their trailers, for one, certainly, and of course there'll be many straight trucks where the cargo box is part of the vehicle. but how they like to operate is really interesting. And I think that if you start walking around these yards, and I've been around dozens of bus yards and coming up equal number of truck yards, how they like to operate is really important to them. So knowing where it's going to be and designing sites around that is yet another one of those kind of certainties. It's going to exist, and therefore they can start to shape their operations to fit.
Very good.
Just to add oh,
go
sorry.
ahead,
just wanted to add the thermodynamic perspective to this question. So, flexibility is key for anything, but it's important to remember that in a case like charging, the waste heat, so the heat that is going to do no useful work in a charge cable goes like the current squared times the length of the cable. So a cable which is twice as long as its neighboring cable will literally waste twice as much heat that does not go to charging the vehicle, that is just lost money and just goes to entropy. So this is an area where we have high leverage to be able to control, not necessarily control, but certainly to suggest uniformity there, so that in the absence of arbitrary random decisions, we can have uniformity, which uniformity is what allows us to drive short cables, which in the end will just mean less loss for everybody.
Yeah, and that's not
for sure. And that goes into the next question we had about the weight of the cable. So if the MCS can be used in the future, how to control the weight of the cable will become very heavy. That was part of the testing we did at NREL. That was one of the big things we were concerned about, the ergonomics of the cable and the connector, and how capable an average user would be to use it. I think we answered those questions. And making sure that cable is relatively short, so it doesn't become cumbersome and heavy, is very important, as well as controlling the heat. And so, which is why we decided and had that big fight about where we put the inlet on the vehicle and why it was so important. Sorry, did someone else have a point?
Oh, this is Andrew. I was just going to add that the cable weight, as Dino was talking about, yes, it's losses on the charging side, but also on the vehicle side, right? We have to carry that weight, and that's additional loss as well that we're trying to minimize.
Yep. The question is, can anyone join to MCS demonstration event in 2021 if registered in advance? Task force members only, but if you are a CharIN member and you wish to join the task force, there was definitely people that participated virtually in the event and watched that did not bring hardware, and that's a possibility. So if you would like to join the task force and work on it and follow the same levels of information security that we all do, then we'd be happy to have you.
Yeah, and
Will MCS?
Oh, sorry.
Sorry, go ahead.
Keep interrupting you. I apologize. I might also add
that okay.
We had international attendance in the first event as well, and so virtualizing it, I guess in that regard, also helps out. Yeah,
we had a couple folks in Europe that were up until the wee hours of the morning on one of the tests. Will MCS also have specific charging time solutions for commercial vehicles? If then, what would be expected charging time compared to current status? So it's just higher power. So right now, what's the fastest charger out there? 350. And so if you're getting up to 1.4, I don't know, Dino, you can do those numbers in your head. How much quicker are we?
It's a more complicated question to give like a realistic answer, because there are battery limits are always going to come into play. But yeah, the answer to this question is actually no. There's no. Let's see, how was it asked specifically? Will MCS also have a specific charging time solution? So I might be interpreting this incorrectly, but there's no requirement there will be no requirement from the standard that says must charge a vehicle in a certain amount of time, and that's because a connector that has a high capability and intrinsically also has a low capability, and the capability is a choice of the end user. Yeah, I hope that's helpful. And then if then, what would be the expected charge time compared to current status? So yeah, in theory, many multiples faster. In practice, battery technologies will dictate how fast it can actually charge.
Yeah, I'll just reiterate, there's no limitation on how slow you want to charge. If you want to charge in an overnight charge slowly, if that's the most economic choice for your fleet, then, and you have an MCS, by all means you can do so, but that also gives you the functionality and the versatility to be able to charge fast when you need to. Will it slow down rolling marine standards? Rolling vehicle standards if aero and marine standards are included. Yes, and so we've really been focused on making sure that we achieve the standards for rolling vehicles, but we are opening conversations with vertical takeoff and landing. If they choose to incorporate MCS in, there's talk of a parallel development cycle using the work that we've done on MCS already. Marine hasn't reached out, but we'd be happy to have that conversation. But we will not delay MCS for rolling vehicles for the other two industries. I will state that. We're already slower than we wanted to be, and we can't afford any further delay. Is there a plan to develop a charging system that caters to battery EVs, hydrogen EVs, fuel cell EVs for synergies? I don't know how you would do that. How is message communication envisioned to be carried from the EV to the charging system? So 15.11.8 for sure. Right now, PLC is the standard by which we are moving forward with, but there are questions as to the capability of PLC to operate under the power levels that we're going to charge with MCS, and there's testing underway that will verify whether or not PLC is capable. If it is not, that opens up the question of what is. So again, testing will let us know. We'll use a scientific method to prove out what it is or is not capable of doing. Question for Kevin: why use deionized water for cooling, as this is aggressive medium for some metals?
Well, the heat pipe that we're using has deionized water as the heat carrying media, and we're open to using other solutions, but our vendor delivers the solution with a recommended deionized water. We do have other options as well, but that's one we're going with right now. Frankly, I'm not aware of deionized water as being aggressive with metals, and it'll prompt me to do some investigation on that. We're not constrained or limited to it, however. And by the way, the amount of deionized water is less than a teardrop full. I mean, it's a very tiny amount of water in the system.
So we answered the previous question on communication. No impact on OCPP. We've said that we'd be OCPP compliant, whether it's 1.6 or 1.8 or 2.0. Any self-reporting of contract conditions or degradation of predictive failure detection? So that is part of the testing that we're planning for round 2. Andrew, maybe you want to talk to some of that repetitive disconnect and connect testing that we have planned out for round 2 for testing at NREL.
Yeah, so we're still working through some of the details, but essentially some of the thought here is that, you know, as the connectors are used in the real world, there'll be corrosion and other contaminants that reduce the effectiveness of the system, and of course we want to be robust to that, and so we're looking to repetitively insert and remove the connector, as well as do some other sort of testing, probably before, but then test it under current and understand the resistance at beginning of life and then end of life or near aged life.
Yeah, we can have some of the participants bring pre-worn parts that have been subject to a number of mating cycles and then test those for resistance.
So I suspect this question is actually reading between the lines about the use case, not necessarily the testing. So if I'm interpreting that correctly, the answer is we expect thermal feedback to be the main feedback for health of the system. Just like basically all connector standards there today, thermal sensing is required. And whether you get into contact degradation, failure prediction is all a matter of how complex you choose to implement the system. But no plans to have any required degradation, accumulation counting, or anything to that effect required within the standard. But thermal sensing, yes.
Thanks, Dino. Apologies if I read that question wrong. I will say I'm the only non-engineer, I believe, on this panel.
I read it the same way, so.
All right, Paul, you're not an engineer either. We're surrounded. Is pantograph charging planned to be eliminated due to MCS? By all means, no. There's definitely applications for Panto. This is not meant to challenge Panto or replace Panto. There's a lot of applications where pantograph charging makes perfect sense. For commercial trucks, pantograph in many applications is just not practical due to what we call packaging concerns. So if you're trying to fit a pantograph on top of one of those beautiful Tesla semis, or one of the the Freightliner semis where we've got all this aerodynamics shaping of the vehicle, there's just no place to put a Panto either up or down on the vehicle. And there's currently no standard in place to transfer power between the trailer and the cab at the levels that would be needed if you're going to put the charging Panto on the trailer. So the best idea that we came up with was a single conductive human or robot operated plug that could conduct this power in the way that we needed to.
Yeah, that's a good point, Rustam, about, there could be other applications for pantograph, but to get to the performance capability, so, MCS is definitely going to be in the realm of capable enough for, larger batteries than we think will ever exist for moving goods around charging at rates which are not yet possible. That can be done with MCS. So in that sense, if your reason for pantograph was because a single conductive handheld plug, you don't think that could handle the required currents, like that's what we've shown to be not true.
Next question, will the MCS be capable of vehicle-to-grid discharge? I'm going to throw this to Paul.
Absolutely not. No, sorry. No, that was somebody else speaking. So a huge vehicle-to-grid fan, and maybe one of the only people in the era when I did had a vehicle that could do that in my own garage. So that's been one of the foundational pieces that I think that I was probably raising my hand and some others. So if you're going to have this capable of a connector, it's just copper, it's just the materials that it is. It'll be equally, a fine piece of gear to go either direction. What you do with it when it goes either direction, how you take it into the building, how you take it beyond the plug standard, that always remains to be a very interesting thing. But by all means, yes, it's set up to, in fact, be bidirectional.
Yeah, that was one of the very first things we wrote down on the board. I believe the very first day we met, we all met and talked about this as what we wanted. It needed to be V2G capable. Maybe to Black and Veatch, how do we actually get the fleet information effectively? I don't understand this question. Did we have exact solutions already?
I'll make up an answer. So what I'm guessing is that they're curious about, okay, well, what is the state of charge in the vehicle? What is the vehicle's preferences, or maybe the user preferences? So the channels of communication, whether the vehicle moves that information via the charge conductors. I'm going to say loosely that ISO 15118 is an opportunity to be able to do that. But while the vehicle is not connected, when it is also important, there's a huge range of via telematics that are part of the vehicle's capabilities already in order to predict and understand what a whole fleet looks like, as well as making some decisions that are not just vehicle-centric, they could be fleet-centric. So if you're going to load balance your fleet, for example, or have a maintenance or cleaning scheduled to one vehicle and need to deplete one and another. So those sorts of things are all understood would probably be add-ons via a fleet management system. In addition, what are those energy needs, and having an energy management system that's orchestrating across the building loads, perhaps batteries, microgrids, planning ahead in the event of a an anticipated resilience event. So lots of communication going on while it's plugged in. Of course, the state of charge is something that the charger is aware of, and what it's able to do with that upstream is generally looked at, and I'll throw it across to others, 15118, to be able to convey that from the vehicle. Ultimately, how it gets there, still some discussions about PLC, as Dino mentioned.
And just as a macro trend related to all this, I saw with interest this week that Amazon Web Services and BlackBerry announced an integrated system around QNX, which is a vehicle-based operating system, and the larger framework of Amazon Web Services for integrating vehicle information, both sort of driving information and while parked information, into a larger IT framework. And I think that, for my money, that's emblematic of the enablement of a big infrastructure for managing data for fleets and individual vehicles. So there's going to be ample framework for deploying great ideas in the future for this. And I'd say they're the fleet specialists, the people who know the key metrics for operating fleets, will have a good hardware framework to work against with people like Amazon and BlackBerry connecting up, and there'll be others as well delivering similar things.
So the next question is one that we actually spent a great deal of time on. Dino, I'll let you dig into this one, because this was, I think, alongside our where the inlet is on the vehicle is potentially our most vehement disagreements we had. Is will there be physical connector and inlet designs for different power levels, or will they, or what's the basis behind having a single design rather than one that's oriented slightly different for different power levels?
Yeah, it sort of gets back to the USB example. You don't want to get in the situation because of the chaos of the transportation, of the realities of transportation. You don't want to be in a situation where you can't plug in. At least that's important right now. And because a higher powered plug can always charge a lower powered vehicle, and a lower powered plug can charge a more like a larger battery vehicle more slowly, there's no fundamental incompatibility there. So as long as we're able to make the MCS plug appropriate for lower power applications in terms of size and real estate, then there was really only a need to have one.
Very good. Question to Dino: does Elon Musk follow closely the MCS development?
Thanks for the question.
No
Tesla specific questions. Thanks.
All right. There we go. What's the roadmap for MCS? So roadmap is next round of testing at NREL, which will be early next year. We were hoping for January, probably now closer into February. And then an additional round of testing of equipment. So the power equipment and the pedestals that take the power equipment, that put the power then through the cable and the connector. And then probably the public release of the design somewhere in between the two of those. So we're going to put a circle on the calendar. Q2 of 21 is probably a good guess as to when the design will be public. That's still subject to a lot of the validation work that needs to be done, but it's a close guess. Anyone want to correct me on that? I saw some heads nodding and shaking.
I was going to just
Andrew,
say,
no?
ready or not,
Dino, no?
get it out there. Yeah, no, it really just the demand and interest in it is very high.
Yep.
And so this session is a great one to get that kind of word out that it's real. I think that's been a question I've fielded a number of times. Is it real? Yeah, it's absolutely real.
Yep.
Where is it? Well, it's coming. It'll be out there soon.
Yeah, I mean, Kevin showed some data, and so did Dina show some data on the first revolution of it, or the first revision that we tested. We're looking forward to testing any additional updates that we want in the second round, and yeah, I expect it to be pretty quick from my side. As fast as the people can provide me hardware, we're ready to test.
And I just want to say I'm really proud of everyone's work in this regard. I mean, these are key members of the task force, but there's other key members of the task force, and we've found that everyone's really come together in a great spirit of cooperation and in an effort to really get this to market in a safe but rapid manner. We all recognize that it's important. We all recognize that it needs to be a global standard. No one wants to have charger standard wars, especially at this power level. And it's important that we get it right, and it's important that we all do it together. So that's the effort, and I feel that we're progressing at the right pace towards the conclusion. So we have good hope and high hopes for it. Question: is there any plan to converge with CharIN, or will MCS stay different? I will say that there have been conversations. We've had exchange of information. We've stayed apprised of the progress of CharIN. I don't think that there is room for a merger just due to the radically different styles of the connector and the communication systems. But I think there's an understanding that there's probably room for both in different markets. But you know, we're, as I said, the effort is to make MCS a global standard for charging commercial vehicles, and that's what we're striving to do.
Can Rustam maybe speak a little bit about what's happening in aircraft on that particular topic?
Sure, go ahead.
That it's frankly concerning, but you know, there's room, I would say, for multiple standards, and usually that follows as it has on a light duty, very strictly geographical regions. If you look at, you know, the ultimate consolidation, I'll say in North America around CCS, you know, you just don't move the vehicles around. Now, aircraft manufacturers by their nature tend to be global, and so there's an ongoing effort that would make CharIN the kind of light duty aircraft activity or potential standard. And so that gets a little challenging if you make and set certain lines, like how many passengers or how much range, because actually those are really loosely defined, especially in aircraft, that the power levels could in fact exceed CharIN's current design spec pretty quickly. And so that it's something I'm monitoring closely, trying to figure out how that'll be synchronized across it, because it's not a crisp, it's got 4 passengers, therefore it uses less, especially if it's an eVTOL, because, for example, they use quite a bit more energy to take off and land. So it's there'll be a lot of conversations in the future. I'll just kind of leave it like that, especially in aircraft.
And that's why we set the levels out that we did. We wanted to make sure that there was some future proofness to the design and the safety of the design, so that when things happened in the future that we can't have concept of now, that this plug would still be a viable standard and useful for charging those vehicles or whatever they are. Dino, maybe you want to speak to that. I know that you stood up in the room and put some of those numbers out there way back when in Detroit, and the room kind of gasped, but I think you were remarkably prescient.
Yeah, I think maybe we set out, we multiplied it by 3 or something, what the like very initial target was. And yeah, and like I said, it was sort of the goal is this is still a plug you can pick up easily and plug in with just a person, and not even a special person at that, just like any person, but still meets kind of every, you know, large vehicle, large battery application that we can think of, projecting it forward as far as we reasonably can. So that's how we came up with the number.
Very good. Final question, I think. Is there any plan to converge with, oh, no, we answered that one already. All right, any final parting thoughts by our panelists here? We're going to start from right to left. Andrew.
Uh-oh, I moved to the right. No, I guess I would just reiterate, some of the discussion in my my slides. We've done some good homework on the design, and we're evaluating it, and the results at this point are looking, very promising, and being able to produce a light connector that you can plug in and charge at multiple megawatts.
Kevin.
Yeah, I would echo similar comments. I'm very impressed by the ability for the diverse team to work together, and has been emphasized by other people. There's a very large number of people on the weekly phone call or weekly phone calls. There are typically 60 with great consistency, and it reflects the commitment and enthusiasm that people have for the day-to-day work and the ultimate goal that is looking to be achieved. And I'm a personal believer in the fact that eventually all electric vehicles will end up being DC connected only. And I'd say this is sort of a step toward the way the world will ultimately be anyway. And and as high performance as the connector is, it fundamentally is an appropriately simple connector as well. So that's really been fun to be a part of.
Awesome. Paul.
So everybody's needing to have a certain amount of patience for this connector to come out, which I know there's a lot of excitement for it. What I would want to leave the the audience with is the connector's going to come out when it comes out, but the planning efforts and securing the fuel that's going to feed this very capable connector can take months and years in a planning. So what I would want to say is don't take your foot off the accelerator on electrification plans, especially when it comes to figuring out how to best utilize this, this new technology and the asset use cases it's going to unlock. The connector is the connector, but there's an ecosystem behind it to give it fuel of the renewable flavor and the grid balanced and all the beauty of those things that are going to take a lot of time as well. So be thinking about the capabilities and planning towards those as a target.
Very good. Thank you, Paul. Dino.
Yeah, I'll just take the opportunity to thank CharIN for creating the space for us to have this conversation and letting it be really entirely, OEM and customer voice driven. So, real voices get through, and there is actual collaboration. It's not entirely political, as these types of groups often can be. So yeah, overall, I've been impressed with how well it's gone and how much actual progress there's been. And yeah, just have to actually thank CharIN for creating that space.
Fantastic, and I would echo those sentiments. Like I said before, I'm really proud of where we're at and how far we've come, and eyes on the prize to get this done rapidly and well. So really want to thank everybody for their time, CharIN and my panelists, as well as all the other task force members included, and really looking forward to bringing this thing to a close and sharing it with everybody, and seeing where we go from here. So, Ricardo.
Yeah, so back again. Thank you all. Thanks to Dino for this kind words. I will take it to the steering committee and the board, of course. Yeah, I hope you had a nice exchange, and so I saw a lot of questions. Maybe we will circulate the unanswered questions through the panelists afterwards. And yeah, for everyone attending, thanks for your time, and yeah, looking forward, as written here, to this to the next stage, and we will closely monitor your activities, guys. All right.
Again.
Thank you. Good night.
Take care. Have a good day.
Bye-bye.
Thank you.
Bye.
Bye.